Hey guys, my name is Ali Alqaraghuli. I'm a NASA Postdoctoral Fellow, and in this video I'm going to explain to you why you probably don't understand the wave equation. In fact, probably a lot of physics teachers out there, a lot of people who even teach physics or explain physics, don't fully understand the wave equation. Or maybe they do, but they don't fully know how to articulate it and get students to get an intuitive and a feeling of the wave equation and what waves even are. So what I'm going to do in this video is explain to you the wave equation, but more importantly, I'm going to get you to get an intuitive understanding of what waves even are. What is a wave and how does this equation describe the behavior or model a wave? And more importantly, what causes a wave? We're going to talk about the cause and effect of a wave. And then finally, I'm going to do something very exciting, which I know some of you guys who are my subscribers are waiting for. I'm going to derive the wave equation from Maxwell's equations. And we're going to talk about the wave equation specifically in the context of light and electromagnetic waves. So let's dive in. There's a lot to talk about in this video, but it's going to be very cool. We're going to start with very easy, intuitive, basic stuff and work our way to the math, which is still going to be very easy and intuitive. So if you're not a physics student or math or engineering student, don't worry. This stuff is still going to be fun to learn about and dive into. So right here, what I have is a wave equation. And again, just to make things simpler, I'm going to erase it and I'm going to rewrite it from scratch. So all the wave equation tells us, and this is the generic propagation wave equation. This is not a specific solution to the wave equation. This is just describing how waves are propagating, like in general, any type of wave. And it goes like this. So we have and usually this is written as like a weird looking d because it's a partial derivative. If you know from my previous video, I like to do English and not other languages. So I'm going to write it as a normal d. Just keep in mind this is a partial derivative. Squared, and we're going to put u. Usually, again, there's a Greek letter, psi, I think it's called, that's used. I'm not going to use that. I'm going to use a very boring English u, just because that's easier for me to understand. So we're just going to describe it as d squared u, and u, again, in this case, is the wave function, or basically the displacement. We're going to talk about what the hell that means in a second. Here is going to be with respect to time. So you can think of this as basically the acceleration. And then on the right side, we have v squared, which is basically the speed of the wave squared. And in this case, we have d squared u, again, the wave function. But in this time, it's not going to be with respect to time. It's going to be with respect to distance x. So this is going to be describing curvature. This is describing acceleration. This is how it's moving or accelerating or changing on the second order in time. This is how it's changing on the second order in space. Now, what the hell do these second order derivatives mean, and why are these here in the first place? We're going to talk about that in a little bit. But first, let's just highlight that there's only really three things to talk about here. There's basically how the wave function itself is propagating with respect to time, how it's propagating with respect to space, and then there's the speed of the wave itself, okay? Now, before we dive into the math, let's get a deeper, more intuitive understanding. What is a wave, right? And what causes a wave in the first place? Well, you can think of a wave as just some type of disturbance in the medium. You can think of a wave as like some really annoying dude who like just goes into like a really quiet environment and just like disrupts things and disrupts the entire environment. So more intuitively, let's use an example over here, which is, let's imagine that we have a little pond or like a lake with just like perfectly still water. You know, we have a pond over here, and then on the side we have like some trees, and then like life is good, you know, everyone's just chilling, having a great time. The water particles are chilling and they're having a great time. And then I come in and I take like a pebble like this and I drop it into this wave or into this pond. What I'm going to cause is I'm going to cause a bunch of waves. I'm going to cause a disruption in the medium, in this case, the water particles. So it's no longer going to look still like this. It's going to start looking more like this. Now, obviously, as you spread over time, this kind of goes and takes a longer flat line. We're not going to talk about that. That's a topic of another video, the attenuation of the wave. But in this case, we're going to just assume the wave just starts rippling, right? So once I drop this thing over here, this wave starts moving in basically all directions within the lake. So that's the wave traveling in space. And that's basically this right side of the equation, which is d squared u over dx squared. So now that this wave is traveling, it's covering ground. And in this case, it's x. Really, it's going to be like xyz, assuming it's like going in all directions. But in this case, we're looking at a single dimension. So let's assume that this is x. This is like positive x. This is negative x. So it's going in all sorts of x directions. It's propagating in space, right? And the speed at which it's propagating at is governed over here by v squared, okay? And finally, this wave is not only propagating in speed, but as time passes, the wave keeps propagating more and more and more in space and in time. Hence, there is this time component, dt squared. So when we take a look at the wave equation, it's actually extremely simple. All we're really describing is that whenever a disturbance happens in a medium, and that's basically all the wave itself is not a physical thing. It is a disturbance. It's an energy that just goes in and disrupts something. In this case, let's say this still water. And the displacement over here, the u, or the wave function, is basically what's happening to the water particles or the water molecules as a result of this very annoying energy coming out of nowhere and just causing disruption. And the result is we have ripples in space, and that these ripples happen over time as well. Hence we have time and we have space. So now I know you might be asking, well, so this is like the wave happening, and Ali, you just dropped something in there and that caused the wave to ripple. But where does the cause and effect actually fall in place? Like, how is this, is this causing that? Is the curvature causing the acceleration? What's actually going on? And in order for us to understand how the cause of a wave is modeled, and actually to get an even more intuitive and deeper understanding of waves and why waves are so unique and cool compared to something like a particle or how we model a particle, let's go and take a look at a much simpler second order differential equation. So we're going to keep this guy over here, and we're going to do something much lazier and much easier, which is going to be F equals ma. Now, this is actually a second order differential equation because the acceleration is the second derivative or the second order derivative or the second order function of position. So if you take position x and you take a derivative of it, then you get velocity, and you take the derivative of that, then you get acceleration. So we're going to rewrite this F equals ma. Well, first of all, we're going to formulate it how I like to think of it, which is A equals F over m. And we're basically going to change this A to be the second order of position. So it's going to be d squared, and here's going to be dt squared, and this is going to be x, okay? So d squared x over dt squared, this is basically A, this is acceleration. And if you take a look, this is actually this is the exact same thing as what's happening. So now we've managed to get both of these left sides to be equal to each other. But you might say, well, Ali, there's a force here, and there isn't a force here. Well, we're going to do something, again, very lazy and very cool that's going to probably annoy some physicists, some mathematicians, is I'm going to just come in and I'm going to add a force, right? I'm going to add a plus F over here. And I'm basically adding an external force to this equation. And why am I doing that? Because without this F, this equation is basically describing the propagation without any initial or boundary conditions. We're not saying where things start or end. We're just describing the ongoing propagation of waves. And later when we talk about electromagnetic waves, I'm going to dive a little bit deeper into that. But basically, I'm going to go ahead and I'm going to add a causal force, which is going to be F. And what I'm also going to do is I'm going to try to keep the F on one side and bring this on the left side as well. So if you know very basic algebra, in order for me to bring this on the other side of the equation, all I got to do is I got to make it a negative. So basically, I subtract this from both sides. And now what I have is I have F equals d squared u dt squared minus v squared du over dx squared. And this is basically a force, and now we have a force. The only difference here, it's my roommate walking by. The only difference here is that, as you can see, we're setting the force just equal to the acceleration, but here it's the acceleration and the position. And this is a very important distinction to understand about waves, is that waves cause a disturbance in the medium, in the entire medium as a whole. It's not causing it in a single particle. When we're looking at F equals ma, such as, let's say, me going in and slapping my wrist right here, I'm attacking a single particle or a single object. Or if we model it like a free body diagram, like some kind of block, and some force is pushing it, we generally treat it as a single object or a single body. But from our example of disrupting the entire pond, we saw that when things are changing in time, they're also changing across the entire space. It's rippling across the entire medium. The wave is disturbing the entire medium. So that's a really unique function about waves. is that waves are going to disturb space and time. They're going to affect curvature and acceleration. And that's something that's very, very cool. So what is this F, you might ask? Well, this is any external force that's going to cause the wave to happen in the first place. And again, this is a simplification. It's an intuitive way to think about it. But for example, in the case of ocean waves, in the case of our little pond example, we dropped something and the waves start rippling. Now, in the case of oceans, there's wind that's causing the transfer of the energy, an external force, which is the wind, that's being absorbed by the water molecules, and the wave itself is being absorbed by the water molecules and starts moving it. Or seismic activity, or plate tectonics. In the case of a tsunami, like some type of earthquake, happens underneath the ocean, and that energy gets absorbed and travels as a form of a wave through the particles, and it sends the water molecule particles soaring. So this is, again, just a very basic idea of what waves are, what causes waves, how are waves behaving. Now let's talk about something a bit fancier, which is electromagnetic waves. And we're going to derive the wave equation using Maxwell's equations. So let's go ahead and do that. So I'm going to go ahead and I'm going to erase what I have over here. And if you remember our good old friend Maxwell, we're going to go ahead and rewrite the equations. So we're talking about the divergence of the electric field, divergence of the magnetic field, B is equal to 0, vector. Now we're going to talk about the curl of the electric field. This is equal Faradays Law. Now we're going to talk about the curl of the magnetic field. It's going to be, let's start with Maxwell. The dE over dt plus, well, it's going to have the mu naught, and this is going to have the mu j. So these are basically Maxwell's equations. We covered these in a previous video. This vector. So, and what we're basically going to go ahead and do is we're going to model this in free space. We're going to model it in a vacuum. Now, what does a vacuum mean? Vacuum means the absence of a medium, absence of charges, absence of currents. Now, for example, this air right now, where I'm sitting in, this is not a vacuum. There's air molecules, there's oxygen, there's all types of other gases, and these molecules and atoms, they are made of particles, such as electrons, which are charged, or such as protons, which are charged as well. And if we remember from this equation, if there is a charge in the medium, that charge is going to cause an electric field. We're going to assume we are in a vacuum, we're in free space. So what that means is there are no charges and no currents. There's no medium that causes a charge to happen or a current to happen. So we're going to reset this to 0 since there's no charges. So again, I'm going to go ahead and rewrite these 4 equations for free space, okay, vacuum. And I'm going to get rid of the current as well, okay? So now we have Maxwell's equations rewritten for free space. And why are we talking about free space? Because we're going to talk about light, and we're going to talk about the speed of light, basically the maximum speed of the universe, allegedly. So now if we go ahead and take a look at these equations, we know that this is Faraday's law. This is what used to be Ampere's law without the Ampere component, Maxwell's law. So we're going to go ahead and start with Faraday's law, let's say. Let's start over there. We're going to begin our derivation. So we are going to do the curl of the electric field is equals to the changing magnetic field with respect to time. Okay, so what we are going to do over here, and again, this is just describing that in order to induce an electric field, the curl of that, you're just going to change the magnetic field with respect to time. We're going to go ahead and take the curl of both sides. And just before you get lost, we're going to do basically a little bit of vector calculus identities and math over here. If this is too advanced, don't worry, we're probably going to cover this in a separate video, but I'm going to try to explain in a simple way how I'm going to derive this. Basically, if I'm taking the curl of the curl, there's an identity over here that you learn about in vector calculus and in linear algebra that goes like this. If you're taking the curl of something, let's say in this case it's E, that basically can look like this. It's the gradient, divergence, E minus the Laplacian of E. Now, if you don't know what the hell the Laplacian is, don't worry about it. It's just basically an operator that when you apply to a certain value, you're establishing its spatial coordinates as second order derivative, second order functions. Don't worry about that. But what we're going to go ahead and do is we're going to replace this curl of the electric field with this new identity. Now, if we remember from the very first Maxwell equation, which has to do with divergence of the electric field, we said in free space, the divergence of the electric field is always going to equal 0 because there's no charge in free space. So we're going to go ahead and apply that here. So this is 0, the gradient of 0 is 0. This entire thing goes to 0. So then we can just replace this entire left side with our negative Laplacian E. So let's go ahead and do that. Okay, and then again, if you're not sure about what just happened, this is basically just an identity of taking the curl of the curl. And it results in this over here. This component went to 0, so now we have the Laplacian. So again, if we go back and rewrite these, so now what's the curl of this derivative? I'm going to go ahead and write this again in a simpler way. Equal to, I'm going to take the derivative out, so dt, I'm going to take the negative out, and now we're just going to have the curl of the magnetic field. Because we have a negative here and we have a negative here, these guys are going to cancel out. So now we have the Laplacian of the electric field is going to be equal to the derivative of the curl of the magnetic field. Now, if you remember from Ampere-Maxwell law, the curl of the magnetic field is basically equal to what? Is equal to, now without the current component, again, we are in free space, this is simply just going to be mu naught E naught times dE over dt. Okay, so the changing electric field with respect to mu naught E naught is going to be that. So we're going to go ahead and replace that in the identity as well. Now this is going to be a dt. This is a dt as well. So it's going to be dt squared, or d squared E over dt multiplied by mu naught E naught. I know this is called epsilon. Sorry, I speak English, not Greek. Here, I'm going to try to squeeze this guy in. So it's equal to mu naught E naught. And so basically, again, we end up with 3 components, which is the Laplacian of the electric field. And we have mu naught E naught, and then we have the second order derivative of the electric field. Okay. Now we can go ahead and rewrite this. If you remember, there's an identity with regarding the speed of light in free space is equal to 1 over squared mu naught E naught. This is basically telling you that the maximum speed possible in free space is determined by the permittivity and the permeability of free space for the electric field and the magnetic fields to propagate. If we go ahead and square both sides, so I'm going to square this side, so c squared, that's going to get rid of this root. So basically c squared is equal to 1 over mu naught E naught. So this can actually go over here as 1 over mu naught E naught, or c squared, and I get rid of it over here. Now if that actually looks confusing, let me go ahead and do it a bit slower. I'm going to write it beneath over here. So again, we have this Laplacian. I'm going to keep it over here, Laplacian respect to E. Instead of mu naught E naught, I'm just going to write 1 over c squared, and then I'm going to keep my d squared E over dt squared. Okay, so now I end up over here. I'm going to erase this guy. We're not done yet. There's one more step, and that one more step, well, there's 2 more steps, is I have a Laplacian, and I still, again, what the hell is Laplacian? Why do I have this del operator squared? This is basically just, again, taking the spatial coordinate of this guy. So this can be rewritten as the second order function of E with respect to, in this case, x. This is for a single dimension. If this was for 3 dimensions, then it would be x, y, and z, and that's going to equal 1 over c squared d squared E over dt squared. We're almost there. And now I'm just going to basically multiply both sides by c squared, and I'm going to bring this side over here. So multiplied by c squared, multiplied by c squared. These guys cancel out. And this guy is multiplied by c squared. And now if you guess what we just ended up with, and we rearrange things, we can rewrite this as d squared E over dt squared equal to c squared d squared E over dx squared. And bingo, if you remember, this is the exact same way, equation we started with, but in this case, instead of E, we started with U, which we described it as the displacement. Now, what does this mean? This means that basically the wave equation is derived from Maxwell's equations, and it's showing you that a traveling electromagnetic wave that has a speed c, which is the speed of light, is nothing but simply the displacement or the disturbance of the electric field alongside the traveling of that wave. And if we go ahead and do the exact same derivation for the other equation, which is the Ampere-Maxwell law minus the Ampere component for current, we're going to end up with the same thing for the magnetic field. So now we know that there's also d squared b, or dt squared, c squared, d squared b, dx squared. And now we have basically two wave equations. One's describing the oscillation of the electric field, one's describing the oscillation of the magnetic field. And basically by combining these guys, we fully understand that the wave equation is basically modeling them as an electromagnetic wave. Now here's the cool part, is if you have light that's traveling in a medium and it's traveling in a certain direction, you're always going to have an electric field component that is perpendicular, and then a magnetic field component also perpendicular to the wave, to the propagation. And this is what the right hand rule is basically, if I'm going in this direction, and then I have my electric field, let's say over here, is going like this, and then I have my magnetic field going like that. So basically you have a wave going like this, electric field going like that, magnetic field going like that, and it just keeps spreading infinitesimally in space, obviously in this case assuming free space. Now it's a bit longer of a video, but I really hope at least you understand waves a bit more intuitively, you understand how we did this derivation, and more importantly, you understand that waves are just a disturbance in a medium, is just energy, and it's causing some disturbance. In the case of optical or visible light or electromagnetics, it's basically the electric fields and the magnetic fields oscillating. And in addition to this kind of fancier way, mathematical heavy way of doing this, we can model waves differently. We can basically model them as sines and cosines, where we have, let's say, y as a function of time and space, has some amplitude, cosine kx minus omega t. This is basically called a harmonic wave. This is a specific solution to the wave equation. If you would like me to cover this in another video, then you can go ahead and leave a comment and do so. And then finally, I want to leave you with a question as well that you can probably answer in the comments if you can. We talked about, for example, in the example of the lake, me dropping something causes things to start rippling. Now, in the case of electromagnetic waves, if I have a flashlight or if I have this watch over here and I press this button and this light starts coming out, what is the cause of this electromagnetic wave to start propagating? If you can answer in the comments, I would absolutely appreciate it. And let me know if you'd like to see a video on harmonic waves or on waves in general. I'll see you guys in the next one. Peace, love.